Okay, so we're going to complete our lecture on unsupervised learning right now with an example of both clustering and PCA. So we talked a little bit about the intuition behind clustering and PCA. They can be motivated through this empirical risk minimization framework. They are motivated via losses. They're just different constraints and different optimization methods. Is what distinguishes clustering from PCA, k-means clustering from PCA. But in a lot of ways, they're very similar. Now, their uses are going to be are quite a bit different. They're used in the same context, and they can be thought of as compression methods. But the way that we use it for exploratory data analysis typically is very different. So we're going to start by working with the Reuters data set. It's just a collection of news articles. Each of these news articles is brief. It's more like a cable, if you will. And we're going to make a vectorization of each of these documents. There's a commonly used vectorization called the TF-IDF vectorization. The basic idea is that the document vectorization, it'll count the proportion of words in a document. And so you have a bunch of documents and you want to turn them, each document, into a vector that can be used in, say, a statistical learning machine, right? And so, so we're going to form a matrix, like a design matrix, Xij, where that number corresponds somehow to the proportion of word J in document I. So if word J does not appear in document I, then presumably that's 0. But how we count proportion is going to change based on the vectorization that we use. The TF-IDF vectorization is sort of a commonly used vectorization. It stands for term frequency inverse document frequency. So term frequency is the proportion of the words within document I, which is word J. So if like the word dog is 5 out of 100 words, then the term frequency will be 5 over 100. Inverse document frequency, there's different ways to count this, but the common way is the log of the inverse frequency of the documents containing word J. So you look at all of the documents containing word J, how much is that as a proportion of all of the documents, then take the inverse and take the log. So that's going to more heavily weight rare words. So if words don't appear in that many documents, then they're going to have a bigger influence on the inverse document frequency, and then you just multiply those two to get the TF-IDF for word J in document I. So the intuition is that you don't want big documents to have just generally larger counts, larger values. You want it to be based off of the proportion of the words that are actually the word in question. So that's the intuition behind term frequency. Inverse document frequency more heavily weights rare words and downweights common words. Okay, so we're going to load in this Reuters data set, and I have my own custom parsing script, but there's a lot of ways to parse this. If we look at it, there's actually different topics associated with each document, and then each document has a bunch of words, and I've removed certain things that are called stop words. This hasn't removed everything that we might want to remove, but we're just going to go ahead with the analysis anyway. If I did a more sophisticated analysis, maybe I would remove things like numbers and punctuation. But for the time being, I'm just hoping that the TF-IDF will take care of this, or that they won't be considered to be influential because perhaps they're so rare that they appear only in one document. Okay, so this is the body of the document, and you could actually read it. This has undergone a little bit of processing, and so you get these extra spaces in between things like punctuation and so on. But you know, for example, showers continue throughout the week in Bahia Cocoa Zone. So this is, you know, most of these news articles have to do with some sort of international trade or mergers and acquisitions and so on, and commodities. So we're going to apply the TF-IDF vectorizer in scikit-learn. This is just it's just a transform, so we can apply the fit transform, and then you just have to give it an iterable of these documents, and the documents, they're just going to split it based on the spaces. So it's just going to take a document like this, split it based on spaces, consider everything in between spaces to be a word, so you get things like periods and punctuation if you don't filter that out. Which I'm just going to sort of ignore that, and then you get this. You end up getting this array. So a couple of things about the array that comes out of this. So there's 1,000 documents in my corpus, and there are in total 10,749 words that appear, unique words that appear in the corpus, and I'm using the word literally. Really, we think of these as tokens, is another way to call them. So the tokens, there's like 10,000 of these. There's far more words than there are documents, and that shouldn't be surprising. If every document gives you at least one new word, then you're going to get more words than documents, and we call it the set of all unique words, the dictionary. And because most words do not appear in a given document, you're going to have that this matrix is very sparse. A lot of its entries are 0. The nice thing is that scikit-learn plays very nicely with sparse matrices. So this actually is outputting a sparse matrix. This is not an array like we're accustomed to. It's a sparse matrix. And you can have access to a full functionality of the sparse matrices in the SciPy sparse module. And you can look more closely at that. So document clustering is the first thing that we're going to do with unsupervised learning. So currently our X, the rows are documents, the columns are words, and each entry is the TF-IDF. So we're going to cluster using k-means in scikit-learn, and very conveniently, this can take in sparse matrices. You can give it a sparse matrix as an argument. And I'm just going to select 10 clusters arbitrarily. I'm just going to use 10 clusters. N clusters is equal to 10 arbitrarily. So we're going to initialize the k-means, and then we're going to fit it, the document cluster, fit it on this X. And now we have fitted clusters. And this is going to run k-means. And the initialization is a random initialization, so that's nice. And now if we, for example, look at the cluster centers, their shape, now we have 10 cluster centers, and these are all vectors that are about 10,000 dimensional vectors. So this should make sense. We should have a bunch of cluster centers, where each cluster center corresponds to a different cluster, and it's a vector in our 10,000 dimensional space. Now with k-means, it's going to find cluster centers which are, averages of all of the elements within the cluster. That's how k-means works. And so these vectors are going to be dense. So this is not going to be a sparse vector. It's not going to look like a document in some sense, in that it is only it's sparse in terms of its word frequencies. It's going to be dense. So I'm going to do a couple of things that are going to allow me to look at these clusters, to explore these clusters. One thing I'm going to do is I'm going to sort the elements of the cluster centers. So if you have a large value for the cluster center, that means the average TF-IDF for the word J. So for example, if you look at cluster center 1, right? If you look at the jth entry of the vector, then if that's large, that means the average TF-IDF for that word J, the jth word, in that cluster is high. So we're going to sort it, and then we're going to look it up, and it sorts in ascending order, so we're going to look it up in reverse. We're going to start with -i, the -ith entry. We're just going to look at the 20 most common words according to TF-IDF within the documents, within the clusters. Sorry. So to do that, I have to create a reverse lookup table, which just allows me to find the ith word in the vocabulary. So the vocabulary here is saved in the IDF vectorizer. So that's what this first line is doing. The second line is sorting the clusters and finding their the indices that correspond to those top sorted entries. And then I'm going to go through and look up the entries in the vocab, the vocabulary words that correspond to those items that are the most prevalent within the clusters. So then I'm going to print out all of the most prevalent words according to the TF-IDF within the clusters. So these are hard to sometimes these are a little bit hard to glean any meaning out of it. But if we look at the first cluster center, we get these abbreviations. A lot of these are like quarter and net, and so perhaps this corresponds to earnings reports. It's not exactly clear. Then you have organization quotas, quota, coffee, meeting, delegates, talks, agreements. So maybe this is international trade. It's not exactly clear, but international appears here. London appears here. Maybe commodities trading, something like that. Then we have another cluster where the common words are issue, bond, priced, lead, manager, payment. So maybe these are earnings reports. Maybe they're currencies. There's euro, bond, franc. So it's not exactly clear. Maybe these are like monetary organizations, and so on. So we can sort of try to glean meaning out of our clusters just by looking at which components are the most common. And this is something that some of this is specific to the fact that we were using a Word document vectorizer. So another thing that I'm going to do is I'm just going to look at the size of each cluster. So I'm going to use the collections.counter object, and it's just going to count the number of times each of the cluster labels. So this labels attribute for the clustering, this is something that we can look at to see what documents belong to what clusters. And so when we look at this, we have that they're actually roughly even. There's not one massive cluster or anything like that, and there was nothing that guaranteed that this would happen. So there are 205 documents within cluster 5, for example, 61 documents within cluster 0. So that tells us a lot about what the clustering is doing. So prototyping. So I mentioned prototyping as a possible use of clustering. So prototyping, the basic idea is we want to find a representative element of every cluster, a representative sample, and that way we can actually just look at that document. And sometimes you can only interpret the actual samples, and it's harder to interpret, for example, the cluster centers, which it is in this case. We've tried to do it by looking at the top most common words within the clusters, but this is what we want to do. So the prototype indices, so the basic idea is we're going to use this pairwise distance as argmin. It's in the metrics module in scikit-learn. And so what we're going to do is find the distance between every cluster center and every x, and then the argmin is going to find the minimizer of this within x. And so if we look at, so what we're going to do is go through these indices, look at the text, and then just print them out. So that's all this script does, is looks at the text. So the first one is we have Dillard Department Stores Incorporated, something about quarter, like the fourth quarter earnings. So this looks like an earnings report is the first one. The second one, we have coffee quota talks continue. This looks like some sort of a international trade and commodities. Next one, we have issuing Eurobonds for this Nederlandse Gasunie, something I'm not exactly sure what this is. So, you know, we can try to interpret what these mean. Some of these might be harder to interpret than others, but this is sort of a way to give representative samples. And we could also kind of associate these with the number of elements in the cluster, saying there's 200 or so articles that are similar to this article in that they belong to the same cluster, and so on. Okay, so I mentioned with the TF-IDF vectorization with word vectorizer or document vectorizers, you can transpose your design matrix, and now the rows are going to be words and the columns are documents. So what is this going to do? Now, when we apply our clustering to this transpose, we're going to be clustering the words instead, based on their document co-occurrence. So if words appear in the same document many times, then perhaps they're going to be more similar. But of course, we're transposing the TF-IDF vector, the TF-IDF vectorized design matrix, and so that's maybe something that we want to think about, whether that was actually a good idea or not. But we'll see if this works or not in a second. So let's apply this clustering. We'll see that this gives some strange results. I tried to apply a standard scalar, for example, to this to no avail. And so I'm going to fit this to the transpose, the clustering to the transpose. And then let's just look at the counts of each label, so the number of elements within each cluster. And what we find is that there's one massive cluster of words. And then there's some very small clusters of words, except for this cluster 2, which has 200 words. So this is something to be aware of. It seems like the words, there's a couple of words that are sort of isolates, and that might not be too surprising, because if a word appears only in 2 documents, then perhaps it's isolated from all the other words in this TF-IDF vector transpose. Okay, so let's look at each of our labels, each of our clusters, and this is just a way to look at the words within the clusters. So I'm going to do this for all but that first massive cluster. This first cluster actually looks kind of promising. Loss, net, operation, profit, quarter, revenues. Revs is revenue, and shares. That looks like earnings reports or something along those lines. Then we have forecast, foreign, Funaro, futures, government, group, growth. It's not exactly clear what this is. International trade, something like that, maybe monetary organizations. And then we have April, California, dividends, Franklin Free Fund, income, insurance, March. So not exactly sure what these are. If there's any real meaning to this at all, it might just be because of the randomness inherent in what documents happen to appear in our corpus. So then we're going to do the same thing using prototyping and just look at the words. And so this was actually a this looks pretty bad. Well, so for the 0th, there's said is the first one, but then said appears again as the closest one for the next for the second index, which that must be some like collinearity or degeneracy that's causing this. So, and then blah appears here. So really, I'm going to think that, you know, if I saw all of this, I would just scrap the clustering altogether. I would say there's nothing substantial coming out of this. I can't glean any information out of the word clustering here. So principal components, so this is the other thing that we talked about for unsupervised learning. Remember, principal components can be accomplished using the singular value decomposition of the design matrix, right? So you can get the principal components using the SVD. So one thing is that getting the SVD for a very large matrix can be very challenging. But if you are only interested in the first K principal components instead of the full SVD, then you can actually do this much more efficiently, and you can actually apply it to sparse matrices, and then the computational complexity will scale with the number of non-zero entries. This is very important to us. So everything that we've seen so far has taken advantage of the fact that the design matrix here is sparse and is a sparse matrix. Every operation is going to be based on some matrix multiply, and matrix multiplies for sparse matrices can be very efficient, are very efficient. And that's no exception for PCA if you use truncated SVD. One of the problems, though, is typically PCA will center your design matrix. It'll center each column of your design matrix before it goes on to compute the SVD. But when you center, then it's going to add a little bit to every single entry, taking those zeros in the sparse matrix to be non-zero. So that's going to make it very dense. And that's going to be a big problem if you want to use the sparsity. So we're just not going to center it and use this truncated SVD, which instead of calculating the full SVD is just going to calculate the top several right eigenvectors of the SVD. Okay, so document SVD, this is decomposition.truncatedSVD. So this is a scikit-learn method that we're going to use. And if we apply fit transform, then it's going to spin out those principal components. Those sometimes we call them loadings, just principal components. The basic idea is if you have your eigenvectors W, then the principal components are what you would get if you took X times your W eigenvector matrix. And you end up getting something that's n by 2 in this example if I make the number of principal components 2. So we can think of these as new variables now for a dimension-reduced data set. So if PCA1 and PCA2 are our new columns for a data frame that we'll construct. Then we're also going to take that document clustering and create a new column for this data frame, which is the cluster labels. Now we can use this for visualization purposes, and this is kind of a typical use of PCA, is we can plot the first principal component against the second principal component, and then I like to use the color to denote the cluster. So you have, this is one isolated cluster, and then you have another isolated cluster here, another cluster over here. And of course, remember, this clustering was done not in the principal component space, but in the high dimensional space. And so other dimensions, other principal components that we haven't calculated here might be having a large influence on these clusterings, which is why you see these overlapping clusters in PCA1 and PCA2. Perhaps if we also plotted PCA3, then you would see the reason for this clustering. So, this is kind of a typical way to visualize high-dimensional data, very high-dimensional data. You know, we took something that was not obviously something that we could visualize as if it was samples in a scatter plot, which is this corpus of documents, and then very quickly we were able to, I mean, really this is just about a dozen lines of code to get this, maybe more, if you streamline this process, to get a very quick visualization of your documents. And if this was an exploratory plot, then you could dig down into what documents are in this cluster and really try to get some understanding of what's going on here. So this is a typical use of PCA. Another thing that was throughout this is very strategically we used the tools and the modules that exploited the sparsity in our large matrix. This would have taken much longer if this was a dense matrix that was 1,000 by 10,000. You know, I was able to do it very quickly on my single machine. That's another thing that's very important. You need to know what is the structure inherent in the data that you're using, and how can you exploit that structure. And that was something that was exploited throughout this example. Okay, thank you.